Oh, do you want to introduce us, Newton?
Yeah, so hi everyone. This is the Ruby Junior Developer Book Club. It's me and Nelson, and this time around, we're excited to have a third member, Miles, who's joining us today. So today we'll be covering chapter 3, and Nelson will be taking us through the chapter. Yeah.
Okay, so in the previous chapters, the book has covered lexing and parsing, and then compiling, and now we're moving on to this part, chapter 3, about running the code. Um, and it's gonna start getting pretty detailed in terms of describing the control structures that Ruby uses to keep track of everything that's going on, because it is a virtual machine and it has to keep track of a lot of things, where the program where you are in terms of which instructions you've run, how many which variables it needs to know about, and other internal things that it also keeps track of. But before we start getting deep into that portion of it, um, I this book is more than 10 years old and it's a little bit outdated. So I want to kind of skip to the section here where it shows a graph of performance. So the performance of Ruby 1.87 versus 1.9. And you can see the graph here where you have Ruby 1.87, and it's actually faster to execute up to around 100,000 iterations. Um, a- and why is that? Um, can either of you to uh, fill in the blanks of why that would be? Why would 1.8 be faster?
Well, I can take a stab at it if unless you want to, Newton.
No, I.
Uh, so I'm surprised that the number is where it is, but my assumption is that it's faster in the beginning. I think he explains this too, but I think it's like running off the parse tree or whatever. It's not going through the compilation phase to the bytecode, maybe. And
Yeah,
so
yeah.
and so basically at some point it is compiled and you're getting the payoff of like each iteration is a little bit faster, but you have an upfront cost for the compilation. But I'm surprised. I don't understand why it takes 100,000 for the inflection point. That part I don't know because I would have guessed it would have been something like 1,000, but it could just be that the compilation is or was pretty expensive.
Yeah, and you have to remember, for any performance graph that you see here, uh, you have to remember that this was done on real hardware. Real hardware then might have been different than the hardware that we run today, because hardware that we run today, processors have, um, there's a lot more technology in terms of branch prediction,
Mhm.
and things could look a little bit different in terms of how fast code runs or not. But in, at least for this graph, in the hardware that where this was run, um, you do have that inflection point at 100,000, and that's because you for the Ruby 1.87, you weren't paying the cost of compilation, and compiling the code does take time. It's got to do some work to transform the abstract syntax tree into some compiled version that can be interpreted or run by the virtual machine. Um, so this book misses out on the recent improvements that have been made. So because of this chart of this graph, where we see, okay, it's faster just like not to run the compilation step if you don't need it. The JIT YJIT was created, and actually it's predated by something called MJIT. MJIT is a just-in-time compiler that is more or less it works on whole method compilation. So if but what happened with MJIT was that it sped up a lot of Ruby programs, but it slowed down Rails.
Mm,
Um,
interesting.
yeah, so it wasn't used a whole lot because of that, because the majority of Rails applications are, uh, 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 sorry, the more majority of Ruby applications are Rails. Um, and so it wasn't, they didn't get the performance they wanted for real world applications. And so Shopify invented YJIT. And what YJIT does is it says, basically, I'm gonna monitor your code execution and um, pay attention to methods that are frequently used and iterations that happen a lot. And when because I'm keeping track of this information, I will know when it's worth the cost to compile some bit of Ruby code. And when I say some bit of Ruby code, MJIT was only capable of compiling at the method level, whereas YJIT is even more granular than that. If if YJIT detects that you have a big switch statement with a lot of conditions in it, but you're really only going through the path with a single condition, like it only hits one of the conditions, can granularly compile just that condition. And because it's not doing the whole method, it's quicker to do. And because it's keeping track of um, the whole application, it only compiles a subset of your entire application, and therefore it doesn't pay as much uh, of that initial cost of compilation, and it has sped things up.
Yeah.
Why?
So
Yeah, go ahead.
I have like two questions. Yeah.
Hmm.
You referenced when you were talking about this graph, you're talking about hardware. And I would want to know like how do you actually generate these graphs, like these performance graphs? Are you isolating each test like to run on maybe a specific machine with a specific version of Ruby, and then after you get the result from that, then you plot everything on a graph, or
Well, they're probably not graphing every possible machine. This is probably a graph taken from a single machine, and we don't know what machine that was. If it's an x86 machine, or if it's an ARM machine, or if it's something else. But it's probably a x86 machine, and it's probably a single machine where they took um, these numbers and plotted them on the chart.
okay. So my other question is this one. You've talked about the initial cost that is paid and how wide it doesn't pay that cost. Yeah,
Yeah.
in the very last thing you talked about.
Mhm.
So I'm trying to get a takeaway, like a takeaway point from everything you said, and I think what I understood personally is that Wygit only compiles what needs to be compiled instead of compiling everything again and again and again.
Mhm.
So if you need, like you referenced the example of a switch statement, those case statements.
Yeah.
So if it needs to compile that, it just compiles that instead of compiling the entire program all over again.
Yeah.
Okay.
Okay, so the initial implementation of YJIT was done in C, but then now it's Rust under the hood, which is super interesting to me. I didn't know that Ruby used Rust at all. I thought it was just pure C. Um, okay, so um, so because we're using YJIT, now we're going to go back to the beginning of this chapter, and so this chapter assumes that all the code has already been compiled, and that's not necessarily the case nowadays. We could still be running from that abstract syntax tree that we created. And by default, the first run, you will be running from that abstract syntax tree until YJIT detects that this code is going to run multiple times and that it needs to be compiled. Um, Additionally, because YJIT is keeping track of this information, it does mean that it's going to use a little bit more memory, a little bit more RAM to keep track of all the statistics that are of which methods are getting called and how many times they're getting called. And so it's going to use like 200 to 300 megabytes more RAM in a big running application like Rails, like a big Rails app. Um, okay, but anyway, so now we can get further into, okay, let's let's assume that uh, that Ruby has already tokenized and parsed our code, and that YJIT has marked this code as running many, many times, and so YJIT has already compiled it. So that's our starting point. And now we're ready to start chapter 3, where Ruby is executing our code. Okay. Um, so Yarv, yet another virtual machine, is going to keep track of. It's a stack-based virtual machine, um, as opposed to a register-based virtual machine. And not only is it a single stack, but it's multiple stacks because it needs to keep track of its own internal state. Keeps track of its own internal state, and it needs to keep track of your Ruby code with your local variables and things. So it's going to keep track of multiple sets of information, and it's going to pile every bit of information it needs into a stack. Um, Miles, do you know what the difference is between a register-based virtual machine and a stack one based one, having implemented one yourself?
Yeah, I mean, I could imagine that. I do believe that the Java virtual machine is register based, and I don't think it has very many registers in it. But like a real machine, like an x86 machine, like real hardware,
Hmm.
would be register based. Basically, there's special pieces of memory really close to like it's like there's kind of a memory hierarchy where the register is at the absolute top, and at the very bottom, I guess you would imagine like a hard drive or something. And there's caching and random access memory and all the stuff in between. But basically, in this chapter, you're going to see them pushing and popping stuff. And
Hmm.
you do that on x86 too. Like, so there's like that program counter, and there's a stack of data, but there's also special registers that you can store data in. And so, like on an x86 thing, like if you wanted to add two numbers, you might have, and I don't remember exactly how the x86 instructions worked back in the day, but you might have to put one variable in a register called like EAX and another one called D, like whatever, like some other name, and then you call an add instruction that knows to add those two numbers. But if there's something important that's already in that register, you have to push it on the stack first. So the process winds up looking like this. There's something important in register A, push it on the stack. If there's something important in register B, push it on the stack. Then put what you really want to add in A and B, call the add instruction, and then maybe the result winds up in C. So backing up, you might actually have to push the contents of C on the stack. And then when you're done, you need to restore A, B, and C by popping back into A, B, and C or C, B, and A. So I guess long story short, I'm picturing this stack-based virtual machine as simply not having any registers. Like all the instructions are going to pop stuff off of the stack to carry out what they need to do and put their result on the stack, as opposed to reading and writing to registers, which would be dedicated, like named dedicated memory, like a tiny number of named dedicated memory locations, is what the registers would be.
Yeah, that's more or less how I understand it as well. Um, the processor also does have its own internal state where it needs to keep track of things. For instance, let's say you add two integers, but and they're 32-bit integers, but uh, the resulting addition creates something that doesn't fit in an integer space. So the processor has a flag, an overflow flag that it sets. And so that overflow flag is basically keeping track of its own internal state. And uh, just because we're using a virtual machine, we don't get away from that. We still have to keep track of, or YARV still has its own internal things that it has to keep track of, but it has to do that in software rather than in the processor. So that's what we'll see here. Okay, so we have YARV's internal stack. We have these are three different things that we're working with here. We have YARV's internal stack, we have a control frame, and then we have these compiled instructions. Um, the and this is uh, already populated um, with the different variables and results that you would get by running this code. Will later on in the chapter, it's going to start with an empty um, stack, and we'll work our way through the code to see what it does. But um, as we run through the YARV instructions, we keep track of the program counter. That's what PC stands for, the program counter. And so the program counter is just basically where we are in terms of running each instructions. We have to keep track of where we are. The stack pointer basically says, okay, this is the last thing on the stack. And I think in partially you have to keep track of this because C doesn't know the length of an array, so the stack pointer is just the top of it, and so this is how many things are there. So the last thing you put in there, or the stack pointer points to the last empty slot that you have in that array. Um, so okay, yeah, I think I've discussed these things. We're gonna get deeper into this chart later on, but basically, you don't just have a single control frame. You have a control frame per context. And what does that mean? What is a context? Well, a context could be you create a control frame anytime you enter a new method, or you can create a new control frame every time you create a block, or at the initialization of your program, there's an eval control frame which starts everything up. And so you're just every time you change each context, you create a new control frame, which has its own internal YARV stack, which has its own set of variables that it's keeping track of um, as we go through the program. Okay. So this is just gonna this section just steps us through how the how everything works, and just the diagram doesn't show it, but we still have a stack frame as an intermediary in here, but we're just the things that it wants to point out only relate to uh, the instructions and the internal YARV stack. So we're going to start at the first trace instruction. I'm not 100% sure what trace means, but that's how that's probably going to be the first instruction of any program is just trace. Um,
It
and
might be for every. Oh, sorry. It might be for like every method or block too. I'm not actually sure. He does point it out in the chapter, but I didn't quite understand exactly what its purpose was. But it might be more than just once per program, but I'm not really sure.
Okay. Yeah, I didn't understand it. Either way, we move on to put self and put self. Every time we enter a new stack frame, we change the context of self, what self refers to. And so every time you call a method or you create a new object, um, those are the few times when self changes, right? Like I am struggling to think of another time when the value of self would change. Um, Maybe when you, let's say, create a lambda or a, but that's maybe that counts
Well, one
as a
that I
new
can
block.
think of, yeah, there's one he mentions in the I was actually curious how this works.
Hmm.
And he mentions that he explains this in a later chapter, I think chapter 8 or something. But one is instance exec, which is just a method where you have a block that was created in some completely different scope with a different self, but you want to run it with the current self, and you can use an instance exec to do that. And it pops up a lot in like metaprogramming.
Yeah.
And I'm curious how that, and I was actually curious about how that works. So I even took a note of it. And then later in the chapter, he points out that he revisits this, I think, in a little bit later. And actually, I think it's gonna, it's not going to be related to this put self, actually. It's going to be, it looks like it works off of the cref thing, which we'll get to later in the chapter, I think. Um, Not really sure, but that's one like real common one in meta programming that happens is the instance exec.
Is it
So,
is it is it the same for its class counterpart, class exec? Does
Yeah.
the same
Ye
apply for class exec as well?
yes, that when you do class exec, you're basically saying run this block of code as if self was this class. Yeah.
Hmm.
So
Okay.
your chain, yeah, exactly. Class exec is the same idea.
um, okay, yeah, you're 100% right, and it's actually something that we stumbled on in the last book that we read, where instance exec does change the value of self. So you're
Yeah.
yeah. Um, okay, so here he says put self pushes the current value of self onto the stack, as shown as figure 3.5. So running put self, what's the value of self on the stack? Um, okay, so we're going to put this object. The object is the value 2 onto the stack. Where next we're going to put another object. That's the um, so the first two is the receiver of the method call, and the second two is going to be the parameter that we give to it. And then as we go through these instructions, um, opt plus is going to be the plus symbol. That's the the method call that we run. After we run the method call to plus these two values, these two twos get reduced to just the number four. And we update the stack pointer. So the stack pointer was here at the uh, the fourth cell, and now the stack pointer is here is at the third cell. Then we send puts the argument that is in the stack pointer. So we send four to the puts. Uh, sorry, we send self the puts method with the argument of four,
Yeah.
and then we leave.
And I
um,
guess the only other thing is that put s like returns nil, which it leaves on the stack. So whenever you like do put S in like IRB or whatever, and then you see nil as the result, that's actually why.
Hmm.
Yeah.
Yeah, that makes sense.
Wait, pardon the reason for leaving nil, the nil you see when you say put something.
Yeah, put S returns nil. So if you do like put S hello world, you should get nil because that's the return value of put S.
Yeah.
So see that nil right there? That nil you see printed there is the nil that's left on the stack after put S runs.
That makes
Yeah,
sense.
that's the one I'm talking
Yeah.
about.
So that
Mm.
nil is the same one you see on the screen on the right there in the bottom cell. So where self used to be, self has now been replaced with nil.
Ah, okay.
Okay, so the first section was assuming that we don't change the context. So that all happened in in a single method. Now we have a block within the method. Um, so executing a call to a block. Now we create we're actually going to have two control frames. One which was our original control frame that we created when we started the program, and the other control frame that we create when we start a new block. Um, and it's basically just going to go through the same process of evaluating the code, um, and creating new control structures for every iteration. So we start with the original code was 10 times do. So I expect 10 additional control frames to be created from this code, one for each iteration. And it's just going to keep adding them to the control frame. I don't know what we call it, a stack control
Well, it would be a
frame.
stack. Yeah,
Yeah.
it's the thing. It's interesting. I would call the thing on the right the call stack, but I don't know what it's called in the Ruby virtual machine, but I would call that the call stack. But um, yeah, so every time you're calling this int due times, you're pushing and popping a frame off that stack to execute that iteration of it. Um, so yeah, that's so remember how they mentioned there were two stacks and they were kind of showing the data stack in the last example, but ignoring this frame stack.
Yeah.
Here they're kind of showing the frame stack, but not the data stack.
Yeah. I mean, it's too much information anyway. It's too much information
Yeah,
as it is. It's really
yeah,
dense.
yeah, yeah.
Yeah. So basically, it's walking through the code, and it's. I mean, we summarized it, so we can just skip this section here. Um, Taking a closer look at the YARV instructions. So the YARV instructions are defined in this file called ins def, and it said there it's not so a C uh, code usually ends in .c. This one ends in .def, and it's because it's not 100% C code. It's C macros that then get converted into C code. And the reason for this, I don't they don't say it explicitly here, but I they do say that they it gets processed when you install Ruby, but it gets processed when you install Ruby because it's got to look at what the hardware you're using, and based on your processor, if it's a 32-bit, 64-bit, x86, ARM, Apple, whatever, it's going to have different machine code that it needs to generate, and so it's going to have different C code that's going to get defined. Um, so at build time, you take the YARV instructions, you run it through a pre-process, and it says mini Ruby here, and I think that's mruby, because mruby can be uh, shimmed inside of C, and
Hmm.
you use it in different places when you want to run Ruby inside, let's say, your game or some other application that uses some other runtime, and you want to be able to call Ruby code, but it's got to be embeddable. So mruby is what you use to embed Ruby in some other larger system that is using some other language.
Mm,
So Dragon Ruby, for instance, it uses C sharp runtime, and the C sharp runtime uses mruby under the hood to evaluate your Ruby code. Okay, so in this process, it throws it through mruby, and it produces this other file, uh, and yeah. Uh, this is just an example listing of what put self looks like. Um, I don't think it's important for us to really understand this code beyond the fact that, like, yes, it's written in C, it gets defined for your machine, and it knows how to produce the relevant C code.
Yeah,
Um,
Nelson.
yeah.
Um,
Oh, we
I've
have 1 minute.
Yeah, that's what I was telling you about. And I have two questions, but I think I'll air them out in the next meeting.
Okay, can you explain to
Yeah.
Miles what we're doing? Because Miles
Oh,
doesn't know
so
what's going on.
yeah, so we are joining another meeting because our time cap for this is done. They usually give
oh,
40
okay.
minutes. Yeah.
Okay.
So there's a link for the other meeting where the link for this meeting was.
Okay.
Yeah, it's named Pacific Time Group.
Pacific Time Group. Okay.
Yeah,
I
Yeah.
might,
you should put it in the
okay.
chat as well.
Okay. Yeah, I'll
Okay.
find it in the chat.
Okay.
Thank you.